Hey YouTube, in this video we're going to discuss what we call partial fraction decomposition, or how to decompose fractions. And actually, before we do that, we're going to preface it with how we compose fractions, or at least put them together. And then what we're really talking about in this video is the ability to take what we get here in this, say, for sum, and rewrite it as its constituent parts as it's written here, to go backwards and rewrite it as this. So let's go ahead and talk about the consequences of adding rational expressions together. The first one is this: you have to have a common denominator. So the first thing I want to do here is establish what do we consider to be the least common denominator for this set of expressions. So here's how you do this. You always factor the denominators when we make this list for our least common denominator. And then you just go through, and I would say that these are all factored already, in factored form. And we say, well, what are the factors? We'll add them to the list, starting with all of the factors of the first expression's denominator. So I notice that x is in its denominator. And as we go from left to right to everybody's denominators here, we're just going to see, are there any things in this denominator here that are not currently on this list? And so I notice that x plus 2 is not on the list. We'd say x plus 2 is now on the list. And going over here, this x minus 2 is also not on my list, so I'm going to add it to my list. This is going to be the value of our least common denominator here. And essentially what we need to do is get everybody to have this least common denominator. So if that's the case, then over here what I'm going to write is like a little underneath here. I'm going to write that I would have to multiply this first fraction on top and bottom times x plus 2 and x minus 2 to get it to have those two factors that it needs in a least common denominator. It's already got the x. So going to the x plus 2, this would need an x and an x minus 2 to keep up with the other two to get this least common denominator. And then over here this would need an x and this would need an x plus 2 on top and bottom. So what we're going to get here is this final overall expression where our least common denominator is the product of the initial two denominators. So x times x plus 2 times x minus 2, three denominators rather. And then we say on top here, well, if I were to take both top and bottom times this pink x plus 2, x minus 2, I would get x plus 2, x minus 2 times 1, which is just itself here. So we say that. Now plus, let's go over to the middle here. If I took 2 times x minus 2, 2x, x minus 2, I would get 2 times x minus 2. And then over here we'd say plus, suppose I write my 4 here, and then 4 times x plus 2. This right here is our sum. It's just that we get to simplify this now. So we now have a least common denominator of x plus 2, x minus 2. It's just that up here we're going to have to FOIL. Looks like here we say x squared minus 2x plus 2x would cancel out. We get minus 4, so a difference of squares. Plus now 2x squared minus 4x when we distribute this 2x here. And then distributing the 4x, we get plus now 4x squared plus 8x. So now combining like terms on the top. Go ahead and go back and do that there. Looks like in terms of total x squared values here, we have x squared, 2x squared, so that's 3 total x squareds, plus another 4x squared is 7x to the second power. And then saying x's to the first, looks like we have negative 4 here and positive 8 here, so positive 4 altogether. And then we'd say minus 4. So this right here, we could go ahead and FOIL out the denominator, but what I want you to see is that this expression that you see right here is equivalent to the expression that we had started with, except for we wrote all of these sums of rational expressions as one giant rational expression. So when we talk about partial fraction decomposition, our goal is to write a fraction as the sum or difference of fractions, other fractions. That's our goal. And so what we're going to learn to do in this video essentially is just decompose the original expression, like expressions you see here, and work backwards to what we started with in the first place. So when we talk about partial fraction decomposition, let's go ahead and start with this. It's the reverse of adding rational expressions. It's taking them apart again. And the concept, we're going to build on this a lot in calculus. So we say the steps for these factors are, first of all, we're going to factor the denominator. So let's go ahead and look at this as we go through the steps for our decomposition here. But essentially we have x plus 7 over x squared minus x minus 6. The very first thing we want to do is make sure that our denominator is in a factored form. And so I recognize that this is x minus 3, x plus 2 as it is in factored form. So when I say write given problem here, it says write the decomposition with variables for constants and different variable over each factors. So essentially what we're going to do is this. We notice that we have this expression here over x minus 3x plus 2. And what I would suggest is that we probably started with now the sum of two fractions, that each of them had their own denominator. So we say x minus 3, x plus 2. We probably started with something like this. So our decomposition works this way. We're going to split this up here, this initial expression, up into the sum of a bunch of fractions. Each fraction's denominator is one of these factors that we see over here. Okay. So we say that the degree of the top expression is always 1 less than the degree of the bottom expression. So since these are both first degree factors, then what we would say is the top here would be a constant thing, or just a constant. So we're going to write A and B. And what we're going to say is this right here, this is what we refer to as the decomposition of our original expression f of x here, where this, we'll call this f of x. Okay. So essentially, when we decompose things, we factor the denominator, and then we rewrite this as the sum of a bunch of fractions, each one's denominator representing one of the factors in the original expression's denominator here. Okay. So things of note, we say if there is a repeated factor, include lesser powers of the factor. So what we mean by this is if we had something like x minus 2 squared, this would be the same thing as x minus 2, x minus 2. So this factor was repeated twice. So if we ever have something like 4 over x minus 2 squared, when we rewrite this, we will rewrite this as a over x minus 2 to the first plus b over x minus 2 to the second. And we have to represent the fact that this could be an x minus 2 to the second or an x minus 2 to the first, but we include lesser powers of the factor. So I include x minus 2 to the first as well as x minus 2 to the second. If this had been x minus 2 to the third, I would have put a denominator with x minus 2 to the first, x minus 2 to the second, and another fraction with x minus 2 to the third. We also say this, if there is a quadratic factor in the denominator, the numerator must be linear. So linear, we say, looks like this, ax plus b would be our linear factor, whereas these are constant factors right here. So we'd say, after we do this, we'll get to the simplified solve for constants and writing the decomposition in the next video, but for right now, I want to be able to write the decompositions. So that's what we're going to do, is we're going to go through each of these, factor the denominators, and rewrite the expression in a decomposed form. So I'd say, factoring this denominator, we get x minus 6 over x plus 2, x minus 2. So I notice that I have two factors in the denominator, and they're both linear factors. So when I rewrite my decomposition here, I would say that I would have x plus 2 in one denominator, plus another denominator here, x minus 2 would be in the denominator. And I would say that these are both to the first power. We had no repeated factors here. And so over here I'd say, well, always on top, whatever we put up here with variable values has to be 1 less in degree than the denominator value here. So since these are both first degree, these will both be constants. We would just write an a here and a b here. Okay. So looking at some more expressions, let's take a look at these that you see here. So this here, we'd start by factoring the denominator. And this one's a little bit more complex to factor. As a matter of fact, I noticed that they have a greatest common factor there of x. So the top we don't need to factor, just the bottom here. And so when we factor this, we say x comes out, we get left with x squared plus 2x plus 1. Now when we factor this, I notice x plus 1 would give me that right there. So an interesting thing happens here. I'm going to rewrite this twice. I'm going to say x plus 1, x plus 1. And I hate to write this again. You got to know that this is killing me right here. But I want to write it this way. And this is the way you'll be seeing it here, most likely. So what I want you to notice is this. When we factored this, we have two factors here. And they're both first degree or linear factors. But what I want you to notice is that this x plus 1, it repeated itself. So when we rewrite this decomposition, the way we're going to write this is over x, this is our first factor here. This one will be over x plus 1 to the first, and this one will be over x plus 1 to the second. Okay, so we're going to include lesser powers of this factor if it's repeated. And then on the top, since all of these are first degree divisors here, first degree factors, then what we're going to say is that the top parts, they're constants. Okay, they're constant things, 1 less in degree than these. So now looking at this one up here, we say factor its denominator. So the first thing we find out is when we factor the denominator, we get an x squared to come out. Oops, no, just an x. So an x, and we get left with x squared plus 1. So now this decomposition, what I want everybody to notice is this. Our factors are x and x squared plus 1, and we can't factor this x squared plus 1 any further. So this is a first degree factor, and this is a second degree factor. So the interesting thing is this. When we decompose this, we're going to put an x here, and in our other denominator, we're going to write our x squared plus 1. But we're going to say that because this is a first degree factor in the denominator, we're going to write a constant on top. But because this is a second degree factor in the basement, we're going to write a linear factor on top. So we're going to say bx plus c. And this is the first time we've seen this, but what I want you to see is that this would be a linear thing right here, whereas this would just be a constant thing. We'd say this would be our decomposition right here. Okay. So for this last example that we see here, let's go ahead and start by factoring the denominator. We still have 3x minus 1 on top, but this time we get an x squared to come out, and I'm left with an x minus 1. So my factors are x squared and x minus 1. So when I rewrite this, here's the interesting thing about this one. That x squared, maybe I'll do this first. It's kind of hard to see unless somebody points it out to you, but at first I'm going to point this out to you, that this is really not a quadratic factor. You would think because it's second degree that it'd be a quadratic factor, but it's really x to the first times x to the first. Or I would never write this on my paper, but I'm going to write it on here because it's notes. We have x minus 0 squared times x minus 1. And what I want you to see is that you have a first degree or linear factor, okay, that is repeated. So when you see this x times x here, when we rewrite this, we're going to write 1 over x, or 1 over x squared. And then the last fraction here is going to be an x minus 1. So here's us repeating or including lesser powers of repeated factors. And on the top, because this is first degree, this factor here is a repeated first degree, we have a constant, and this is a first degree thing, so we also have a constant. This would be the decomposition right there. So when anybody refers to partial fraction decomposition, basically it's this part right here where we're just rewriting it decomposed. Cheers.